There is a road in America where, for 8 straight miles, you cannot see land in any direction, not behind you, not ahead of you, not to either side, nothing but flat open water stretching to the horizon. And the strangest part is that road was built in 1956 by men who had no GPS, no computers, no satellites, and no blueprint to copy from, because nobody on Earth had ever tried to do what they were about to do. And by the time this video ends, you will understand exactly how they pulled it off and why, 70 years later, not a single section of it has ever had to be replaced. This is the story of the Lake Pontchartrain Causeway, 24 miles of bridge laid directly across open navigable water, still officially the longest structure of its kind on the planet. And the reason it exists at all comes down to one unbearable daily reality for tens of thousands of families in the early 1950s. New Orleans was booming, jobs, housing, opportunity, all of it pulling people toward the city. But if you lived on the north shore of Lake Pontchartrain and needed to get to work on the south side, your commute wasn't a drive. It was an expedition, a 90-minute crawl around the entire perimeter of a lake covering more than 600 square kilometers, meaning a simple trip to work and back home again could eat 2 full hours out of your day, every single day, for as long as you lived there. 40,000 families were living with that exact math, and city planners knew something had to give. The obvious answer seemed simple enough on paper. Build a bridge straight across the lake instead of driving all the way around it. But here's the detail that made this project unlike anything American engineers had faced before. A river, no matter how wide, is narrow enough to anchor a bridge against, predictable enough to model, contained enough to control. A lake of this size behaves completely differently. In a serious storm, Lake Pontchartrain doesn't ripple, it rages, moving like its own furious, self-contained ocean. And any structure built across it had to survive that violence indefinitely, not just on the day it opened, but for generations afterward. So in 1952, engineers went out and started taking soil samples from the lake bed, expecting, at worst, some manageable variation in ground conditions. What came back instead stopped the entire project cold for almost a full year. Beneath the water sat roughly 30 feet of soft, organic mud, sediment built from thousands of years of decomposed vegetation, and its bearings capacity was close to 0. This wasn't simply soft ground. It was ground that behaved almost like a liquid under load, shifting the instant any real weight or vibration was introduced. Engineers testing early pile drives watched in disbelief as some piles didn't sink gradually the way they should have. They simply vanished, swallowed whole into the mud in under a minute, gone, along with the equipment and the time it took to lose them. And the borings kept confirming the same. Grim pattern no matter where crews tested. This wasn't a localized problem in one unlucky spot. The unstable mud layer ran for miles in every single direction beneath the lake. Every boring result that came back pushed the projected cost of the entire project higher, and for a while it genuinely looked like Lake Pontchartrain might simply refuse to be crossed, as if unstable ground beneath 30s. Feet of water wasn't punishing enough? The lake had one more trick reserved specifically for the men working in the middle of it: sudden, total, disorienting fog that could roll in without any warning at all. Picture a barge. Crew stranded in the exact center of the lake when that fog descends. No land in sight to begin with, and now 0 visibility on top of it. No landmark, no shoreline, nothing but the sound of water and a compass in someone's hand, because navigation out there was entirely manual, position estimated by feel and instinct, and a single miscalculation in that fog meant driving an expensive precast. Pile into completely the wrong spot in open water, with no easy way to know it until it was already too late. Despite every one of these compounding problems, the Louisiana Bridge Commission moved forward anyway, hiring Majeski and Masters, one of the most respected bridge engineering firms operating in the country at that time. And construction was formally authorized in 1953 with a budget of $30 million and a deadline that everyone understood without it ever needing to be written down. Get this done fast, because families were waiting. Work began not on the water, but on land, at a new construction yard established in Metairie, because the design team had already made the single decision that would define the entire project. Instead of pouring wet, concrete out in the open water, a method that would have been dangerously slow and unpredictable given the conditions. Every pile would be precast on solid ground, cured to full strength before it ever touched the lake, and then floated out on dedicated supply barges to its exact final position. Each of these piles measured 16 inches square and stretched 54 feet long, reinforced with pre-stressed steel inside, and the project as a whole would ultimately require roughly 9,500 of them driven into the lake bed. Separately, massive concrete pile caps were cast on land as well, engineered collars whose entire job was to transfer the load of the roadway beams directly down into the top of each individual pile, and every single one of these components was physically inspected on shore before it ever left for open water. Supply barges moved constantly back and forth in convoy, feeding a purpose-built pile-driving barge designed with an unusually shallow 1-meter draft specifically, so it could operate across the lake's wildly inconsistent bottom depths without running aground. But precision out on open water turned out to be its own nightmare. Every pile had to enter the mud at exactly the correct angle, and even a deviation of just 2 degrees would mean the finished cap simply wouldn't seat properly against the beam above it. Crews would drop the hammer, expecting the pile to punch straight down, and instead watch the soft mud rotate it sideways instead of accepting it cleanly, an infuriating, expensive problem that sent engineers back to the drawing board not once, but twice, redesigning the guide frames that were supposed to keep each pile aligned. What had worked perfectly during land-based testing kept failing out on the water, because nobody had accounted for how much the barge itself would flex and shift under lake swell during the actual drive. So the crews adapted the only way they could by measuring obsessively, tracking exactly how far every single pile moved with every single hammer blow, and whenever a pile drifted off angle in that soft upper layer of mud, they simply pulled it back out and redrove it from scratch. A process that could burn hours per pile, and out here, every single hour mattered enormously against the clock. The entire purpose of all that effort was to punch straight through the unreliable upper mud and seat firmly into a layer of stiff clay sitting roughly 50 feet down, because that clay, the mud depth varied constantly across the site. The resistance varied with it, and nothing about this lake bed was ever consistent enough to simply repeat a formula. By early 1955, despite every obstacle, the pile line was steadily advancing further into the lake, crews averaging roughly 1 complete span every 2.5 days, a pace that sounds modest until you remember they were solving a brand new engineering problem essentially in real time, with each span built almost entirely by hand and by feel. Once a section weighed a staggering 60 tons, set into position out on open water with a placement tolerance of only half an inch. Grout was then used to permanently lock every beam to its cap, and if that joint wasn't filled correctly, the consequence wasn't cosmetic. An improperly sealed connection meant movement under the weight of traffic, and movement repeated enough times meant slow fatigue failure that could compromise the entire structure years down the road. To keep pace with the sheer volume of concrete this project demanded, engineers set up something almost unheard of at the time, a floating precast yard positioned in the middle of the lake itself, where concrete was mixed, formed, and cured directly on the water, rather than shipped out from shore every single time. Crews were literally pouring concrete on a barge that never fully stopped moving, meaning even a small swell rolling underneath could subtly alter the pour angle of every single form on board. There was no ducking back to shore for lunch out here either. Workers lived aboard vessels in the middle of the lake for weeks at a stretch, existing in a strange, isolated world with no exit, no road, no hospital, no town anywhere nearby, meaning that if something went seriously wrong out there, help was realistically hours away no matter how urgent the emergency. Each completed section of deck simply became the working platform for building the next one, the bridge quite literally constructing itself forward, span by span, meter by meter, out across open water. Heat, glare, and disorientation were a constant companion for every worker on site, so crews rotated off mid-lake duty every 10 days just to preserve their sanity and safety, while night shifts continued running through good weather to keep the schedule alive, and construction only paused entirely when wind conditions made operating the cranes genuinely unsafe. Add it all up, and the pace becomes almost unbelievable. 24 kilometers of bridge completed in just 14 months. Which works out to roughly 58 meters of finished structure appearing over open water every single day, using nothing more advanced than 1950s-era equipment and pure human persistence. By the middle of 1955, the entire southern half of the crossing was complete, while a separate crew working from the north shore near Mandeville pushed steadily toward the middle to meet them, and this is where an entirely different kind of precision mattered enormously. Because these two construction fronts, approaching from opposite ends of an enormous lake with no satellite positioning available whatsoever, had to meet in the exact right spot, since even a single degree of angular error at the starting point would compound over miles into a permanent, unfixable misalignment. Engineers solved it using optical triangulation, measuring precise angles back to fixed monuments on shore. Essentially, pure geometry executed entirely by hand, and remarkably, it worked exactly as intended. One additional feature was built into the design as well, a drawbridge span providing roughly 8 meters of clearance so that sailing vessels could still pass through the lake freely, with a bascule hinge mechanism engineered to withstand decades of relentless salt air and humidity without failing, a promise that has held true for 70 years and counting. Handrails, expansion joints, and the final road surface were then fitted section by section directly onto the completed grid of pile caps, with those expansion joints serving as the bridge's essential pressure relief valves. allowing the entire structure to flex safely with every seasonal temperature swing rather than cracking under the strain. Finally, in June of 1956, the southbound span officially opened to traffic, and drivers could now cross the lake in roughly 23 minutes flat, a number that instantly rewrote what commuting around Lake Pontchartrain even meant. On opening day, something remarkable happened. Drivers slowed to a crawl. Some of them stopped entirely in the middle of the bridge, simply because they had never in their lives driven across open water with no land visible anywhere around them. And Guinness confirmed almost immediately what everyone already suspected. This was now the longest bridge over open water anywhere on the planet, a record Louisiana would go on to hold for decades. That very first toll to cross the bridge was 93 cents, and for many working families in 1956, that represented close to an hour's worth of wages. Yet people paid it gladly because the bridge had permanently changed the basic math of daily life for an entire region. Not everyone adjusted easily, though. Some early drivers reportedly experienced genuine panic attacks partway across because flat water stretching endlessly in every direction can trick the mind into feeling like you're driving straight into open sky, and the physical bridge itself did nothing to soften that sensation. Bare concrete deck, no shoulders, no median strip, just two narrow lanes with barely enough room to safely stop if anything at all went wrong. Within only 3 years of opening, the ocean air had already begun quietly attacking the concrete, because chloride intrusion from salt air is a slow, patient, relentless process that never fully stops working against a structure like this. Engineers had calculated wind loads carefully during design, but nobody had specifically modeled what would happen if the bridge took a direct hit from a full hurricane. And in September of 1965, they got their answer. Hurricane Betsy made landfall with sustained winds battering the causeway at speeds exceeding 120 miles per hour for 6 continuous hours. And when the storm finally passed, inspectors found 17 spans damaged, several deck sections physically displaced, and the drawbridge span knocked completely off its seat. Engineers reached the site within 48 hours of the storm passing, and what they documented that day would go on to change every single specification used for the bridge's future northbound span. The good news was enormous. The original pilings held firm, and the original pile caps held firm too, meaning the foundational engineering from 1955 had proven itself under conditions nobody had originally designed for. What failed instead were the connections between the beams and their caps. The beams themselves had simply slid off during the violent wind loading, and Hurricane Betsy delivered one blunt, unmistakable lesson to every engineer who studied the aftermath. Weld everything down permanently. Don't rely on gravity and grout alone. Every single beam tie on the surviving southbound span was retrofitted before the bridge reopened to traffic, and Betsy's damage effectively became the design blueprint for an entirely new northbound span, where every point of failure identified after the storm was rebuilt from the ground up as a hard engineering requirement rather than an assumption. From the outside, that second bridge looks almost identical to its older sibling, but internally, the structural connections holding it together are fundamentally different, built specifically to survive exactly the kind of failure that Betsy had just exposed. Construction on the northbound span began in 1967 with engineers tightening pile spacing across the new structure and adding steel dowels directly to the top of every new pile cap so that beams could be cast solidly around them, forming one continuous unified connection rather than a stacked assembly vulnerable to sliding. Cap width increased by 14 centimeters as well, a change that sounds minor on paper but becomes enormously significant the moment a 12-foot storm surge slams into the structure. For 2 full years, regular traffic continued crossing the original southbound span, while the brand new northbound span rose right alongside it. Meaning, for a stretch of time, an entire second bridge was under construction directly beside a fully operational one carrying live daily traffic. By 1969, laser alignment technology had become available for the first time, and the northbound span became one of the earliest water crossings in the entire United States to use it, achieving millimeter-level positioning accuracy across distances of 3 kilometers. A staggering leap forward from the pure hand-measured optical triangulation used just over a decade earlier on the original span. The northbound beams themselves were redesigned to span longer distances between piles, requiring fewer total piles per kilometer while simultaneously carrying a higher rated load capacity than before, and the road surface was upgraded from bare concrete to a textured aggregate finish, offering noticeably better grip during rain and the lake's notorious sudden fog. The final pile of the northbound span went into the lake bed in 1968. Bringing the combined total across both structures to more than 14,000 piles driven into Lake Pontchartrain, and when the northbound span officially opened in 1969, the crossing's total capacity effectively doubled overnight to 4 full lanes of traffic. The ripple effect on the surrounding region was almost immediate and undeniable. Once both spans were fully operational, the population of St. Tammany Parish on the North Shore doubled in less than a decade. a transformation driven entirely by the existence of this one bridge. But building it well was never going to be enough on its own, because Lake Pontchartrain continued producing its signature radiation fog with almost no warning whatsoever. Cold air meeting warm air and dropping visibility to near zero within minutes. So engineers eventually installed visibility sensors every single mile along the entire 38-kilometer span, feeding a control center that monitors every sector of the bridge simultaneously around the clock. The rule engineers settled on decades ago has never once been softened. The moment visibility drops below 200 feet anywhere along the span, the bridge closes completely, no exceptions, and it only reopens once every single monitored zone clears at the same time, even though that closure inevitably backs traffic up for miles in every direction. For decades, every crossing was logged manually, and toll revenue was funneled directly back into ongoing maintenance, meaning this bridge has effectively paid for its own upkeep since the very day it opened. Salt, sediment, and floating debris accumulate constantly against every submerged structural element, making marine maintenance not some optional afterthought, but the literal reason this bridge is still standing 70 years later. Divers descend regularly to inspect every single submerged pile by hand, checking specifically for spalling, hairline cracks, and any sign of exposed rebar, because chloride that seeps into even the smallest crack will quietly corrode the steel reinforcement hidden inside, and left uncorrected, that corrosion eventually splits the surrounding concrete apart from the inside out. Damaged piles receive targeted epoxy injection repairs, followed by a fiber-reinforced polymer wrap, and this maintenance cycle runs continuously, year-round, without pause. In 70 full years of operation, not one single span section has ever needed to be replaced outright. Targeted repair has always proven sufficient. And, remarkably, some of the original 1956 handrail sections remain in active service today, marine-coded and still fully compliant with modern safety standards after 7 full decades of exposure. On an ordinary day, peak traffic flow hits between 8 and 9 in the morning heading southbound, with the bridge handling substantial volume in both directions simultaneously. But the single most dramatic test of everything these engineers had built came in August of 2005, when Hurricane Katrina made landfall as a powerful Category 3 storm. Storm surge on Lake Pontchartrain reached 12 feet above normal levels, and the entire north shore flooded completely. Mandeville, Covington, and Lacombe all submerged beneath rising water, with both approach ramps on either end of the causeway completely underwater. Engineers couldn't even reach the bridge by conventional road. They had to travel out to it by boat 3 full days after the storm had passed. And what they found once they arrived genuinely surprised almost everyone involved. There is still a visible line on the structure today marking exactly how high Katrina's surge reached, a point where the bridge deck itself sat briefly under roughly 2 feet of storm surge. Yet once crews cleared away the mud and debris left behind on the surface, they found zero structural damage anywhere below it. Every pile cap remained properly seated, every beam remained securely tied down, everything held exactly as engineered. All 2,243 individual spans across the entire crossing were inspected in the aftermath, and every single cap was confirmed seated, every single beam confirmed tied. The causeway reopened to emergency traffic within just 3 weeks of the storm, becoming the very first road link restored back into New Orleans after Katrina's devastation. Without that restored crossing, rescue convoys attempting to reach the city would have been forced onto flooded surface routes that would have added hours to every single trip, hours that desperate people simply did not have to spare in that moment. In the days immediately following the storm, thousands of people actually walked across the bridge on foot, a use case the structure was never remotely designed to handle, and it carried that unplanned foot traffic without complaint regardless. Aerial footage captured in the aftermath shows the causeway standing out as the only completely dry road connecting the flooded city to the outside world, making it, quite simply, everything to the recovery effort in those critical early days. Notably, it was the approach ramps on either end that took the longest to clear and repair. The open water spans themselves fared far, better against Katrina's fury than the land-based connections leading onto them. Inspectors confirmed that the original 1956 piles showed zero structural compromise anywhere after the storm, and Louisiana's Department of Transportation and Development ultimately declared Katrina a complete real-world validation of the entire original design philosophy, proving conclusively that engineers working back in 1955, armed with nothing but hand calculations and raw persistence, had gotten the fundamentals exactly right. Today, roughly 42,000 vehicles cross the Lake Pontchartrain Causeway every single day, and remarkably, it never fully closes for scheduled maintenance. That work instead happens continuously under live traffic, with lane closures planned down to the exact minute specifically to keep normal flow moving smoothly during peak commuting hours. The Greater New Orleans Expressway Commission now operates the bridge around the clock with a dedicated staff of roughly 250 people connecting Metairie and Jefferson Parish on the south shore to Mandeville and St. Tammany Parish on the north, spanning 23 miles of essentially uninterrupted open water. At roughly the 12-mile mark, there is no land visible in any direction whatsoever, arguably the single most complete experience of open water isolation available anywhere on an American highway. Every mile marker and every painted road line along the entire span gets fully repainted on a strict 3-year rotation, with the same dedicated crews cycling through the full length of the bridge again and again. China's Jiaozhou Bay Bridge eventually claimed the title for longest bridge overall back in 2011, but that structure crosses primarily on elevated viaducts rather than truly open navigable water, which is precisely why the Guinness World Record classification for the Lake Pontchartrain Causeway has never changed. It remains, to this day, the longest bridge over open navigable water anywhere on the planet. Virtually every long-span water crossing engineered anywhere in the world since 1956 has borrowed at least some technique first worked out right here on this lake. Whether that's precasting components on land, floating them into position, or the sheer discipline of measuring obsessively when no automated system exists to double-check your work. The man who directed this entire original project, Emmett Harrington, went in as an administrator and came out, by every meaningful measure, as a builder who had solved a problem nobody else had ever attempted. The original South End toll house from the very first bridge was deliberately preserved even after electronic tolling fully replaced manual collection back in 2014, standing today as a quiet, concrete footnote to how far the crossing has come. Modern acoustic testing technology now allows engineers to confirm the structural integrity of individual piles without any excavation or diving required at all. Sound waves are simply sent traveling through each pile, and the signal that returns tells the truth about its condition. And after 70 years, sitting in a saltwater lake, that signal keeps coming back clean, test after test, year after year. This, ultimately, is what engineering without any safety net truly looks like. No computers to model the stress, no GPS to confirm position, no backup design waiting in reserve if the first attempt failed. Just 14 months and exactly one real chance to get it right. 24 miles of bridge, 2 full spans, roughly 14,000 piles combined, 70 years of continuous service, and not one single structural failure across the entire history of the crossing, still standing today exactly as intended. The men who built it are almost entirely gone now, but their work quietly carries 42,000 vehicles across this lake every single day without a second thought from most of the people driving over it. The original south span cost $46.8 million to build, with another $30 million spent constructing the north span years later. And the true value of what that investment ultimately delivered is, at this point, simply impossible to calculate. Those very first drivers crossing in 1956 had absolutely no idea they were driving over what would become one of the most technically original pieces of infrastructure in American history. And today's drivers cross the exact same lake in roughly 20 minutes without giving it a second thought, which is, in its own strange way, the clearest possible proof of just how completely this engineering succeeded. It was built by men who trusted their own mathematics more than they feared an unpredictable lake with no precedent to guide them. And in 70 full years, that lake has never once proven them wrong. If you have ever driven across this bridge and felt absolutely nothing unusual at all, if it simply felt like any other stretch of paved road beneath your wheels, understand that this is precisely what extraordinary engineering is supposed to feel like. And if this story of impossible mud, invisible fog, and a bridge built without a single modern tool made you appreciate what these men actually accomplished, stay subscribed, because there are far more stories like this one still waiting to be told.